Let's see.
Yeah.
And then we finally managed like to
You mean that helpful? Yeah. Check. Did you go? Also go.
How can you tell?
You need to solve it.
All right, I think we're good to start. Today we have Michele Mancarella here from the University of Geneva to talk to us about gravitational wave cosmology with dark sirens. So take it away.
Okay, thanks. So I'll accept the invitation. Got it. Okay, great. Let's get started. So thanks a lot for having me. It's well, it's a real pleasure to be here live. Actually, it had been a while, and yeah, also to see people facing a storm. So today I'm going to be talking about gravitational wave dark sirens, so sources without a detected electromagnetic counterpart, and how we can do cosmology with them, and recent applications to data, and some hopefully nice perspective of this field. So the talk is going to be divided basically in three parts. I'd like to start with an introductory part to set up some basics of gravitational wave cosmology and applications, so how we can measure the Hubble constant, test gravity, and then move to the real concept of dark sirens, connecting them to statistical methods. The second part will be dedicated to show some applications to the latest data releases by the LIGO Virgo collaborations, and then in the last part I'd like to discuss a bit the future with a focus on ground-based detectors. Okay. So starting from the very beginning, let's see. Now, let's start really with the gravitational wave binary, okay? We can compute the signal it emits, and let me remind the basics. So the important things are we have two polarizations called the plus and cross. They share a common amplitude, which depends on a mass scale called the Chirp mass of the system, which also enters the phase. And the two polarizations differ for a function that depends on the inclination of the binary with respect to the line of sight, denoted by this iota here, and then there is an inverse distance scaling in front. So this solution is known. Of course, now, if the source is at cosmological distances, what we have to do is to check how it propagates up to the observer, right? And this takes place in a Friedmann-Robertson-Walker universe, and restricting for a moment to general relativity, we have a propagation equation for the two modes, okay, which is given by basically a wave equation with a friction term, which is given by the Hubble flow. Now, I'm sketching quickly how do we get the scaling of this wave during this propagation, because it's going to be very useful in 5 minutes. And the idea is very simple. We have this equation, and we would like to get rid of this friction term to solve it simply. So what we do is we rescale the perturbation by the scale factor. And this way, we basically get an equation for this new variable, which for modes well inside the cosmological horizon is a wave equation. Okay, so when we go back to the perturbation we are interested in, we get basically a plane wave with a shifting amplitude. So this is named as the inverse scale factor of the universe. Nice. Then the second thing we have to take into account is that, of course, during the propagation, the time after propagation, the time will be measured in the observer's clock, and the frequencies will get redshifted the usual ways. So let's consider this effect as well. And when we plug all this in the original signal, we learn a couple very important things. Okay, the first is if we look at the mass. So the thing is that all these redshift dependencies get completely reabsorbed in a shift of the mass. Okay, so now the mass enters always here and there. Unfortunately, the color choice is not optimal for this projector, but it's the product of the chirp mass times 1 plus the redshift, which we call detector frame mass in this case. And this is what is measured by the waveform. Okay. The second thing is that in front here the distance scale is what we call the luminosity distance to the source. So really the ratio of fluxes that you would find from electromagnetic observations. Okay, so that's that was a simple derivation, but it's it contains a lot of information. And so now let's consider the scenario in which we want to measure this thing. Okay, there is the nice thing is to consider the ideal scenario. Now we have two polarizations, so we can imagine we measure them. We can take the ratio, and the ratio will fix this function of the inclination. So we will know the inclination. Then we can measure the phase of the wave, which actually determines very precisely the redshift, the chirp mass. So we will know that. And now the amplitude of the signal leaves us with the luminosity distance. Okay. So all this is great, but of course in practice this is a super complicated parameter estimation, because what you rather measure is a complicated projection of the two polarization on the detector plane, depending on how the detector is orientated with respect to the source and all sort of complications. But so rather than having a clean value, you will have a distribution of this quantity with an error, but the luminosity distance is a parameter of the waveform, and you get directly from analyzing the signal. So this is a bit the first or the pillar of gravitational wave cosmology, if you want, because now we have a direct distance tracer, which for cosmology is rather unique, and this is the reason why these sources are called standard sirens, because now, of course, cosmology is a lot about comparing distances and times, usually in the form of redshifts. And so if I write explicitly the expression for the luminosity distance, this will depend on the way the universe expanded during the time the signal reached us. So in particular, it will depend on the matter and the energy or dark energy content, and of course on the famous Hubble constant, because this low redshift is nothing but the Hubble law. Okay, so this is the first important thing, is now we can measure the expansion of the universe in a completely complementary way to electromagnetic information. Okay. Right, so that's and of course this is not relevant now. This is a bit of a spoiler of the results, but we have measurements from CMB, from supernova. They are intention, so the goal of the community here will be, these are the error bars on gravitational wave measurements. So the idea is, will they align on one or the other side? Okay. Okay, great. However, that's this is all very important, but it's not all we can do with these sources. And the reason is actually related to the propagation of the wave through an expanding universe. So now I motivated the DL scaling using basically this equation in general relativity. But a major goal of cosmology in the next 10 years or so is actually precisely to test this equation. So to check if at cosmological scale this is the way tensor perturbations propagate. And so after the journal club you had half an hour ago, I should start seeing people shaking on their chairs, because of course there are other possibilities, and in particular a possibility that is still allowed by data is that the friction experienced by this wave is not given by the pure Hubble flow, but has an additional contributions that in modified gravity scenarios, so when you add degrees of freedom to GR at cosmological scales, typically arise in this form. It's a property of basically any modified gravity model on the market. So now I would like to check how this wave scales during propagation. And of course, you remember the trick was a simple idea. No? I want to kill this term, so I redefine a rescale perturbation. But now to do this thing, of course, I cannot use the same scale factor that I used before because this is modified. Okay, so I can still redo it, but the way I do it will be with a different function from the GR case. Okay, now defined by a different equation written here. If I do this rescaling, I will still get a wave equation. So my original perturbation will still be a plane wave with redshifted amplitude, but now the factor in front here will be different from GR. Okay, and the difference will be actually encoded in this friction term, so I can compute what this new distance notion is, and this is what has been defined by the community as gravitational wave luminosity distance. So now, if you allow for the possibility that other degrees of freedom are present, this is really what is measured by the gravitational wave experiment, and we can relate it to the usual notion of the luminosity distance by basically integrating this equation here. And now I marked EM here to say electromagnetic to stress the fact that this is really what you will get from the same source by measuring the electromagnetic signal. Okay. Now we have this effect. Just before moving on, last thing I wanted to say on this, it's how do we test it? So for people, for experts in constraining dark energy, etc., a general strategy, let's say, to constrain deviations from lambda CDM in cosmology is that you find physical effects related to the presence of extra degrees of freedom. You parameterize them and you constrain the parameters, roughly speaking. So this is what we do. For example, at the background level, we will have an evolving equation of state for dark energy. We parameterize it with W0 WA, which we can test with the CMP, etc. In the scalar sector of perturbation, we could say, for example, the Poisson equation gets modified so in such a way that, for example, what we call the Newton constant becomes a function of time, and we can constrain this evolution. And so the exact analog of this in the tensor sector, which we need to complete the picture, is this phenomenon of modified gravitational wave propagation. So the idea is to introduce a parameterization which is a bit the mirroring what we do in other sectors, and this is the side 0n parameterization. So the idea is to parameterize directly the ratio of gravitational and standard or electromagnetic distance.
Sorry, just a very stupid question. So why this distance is not the same for electromagnetic waves, since they also propagate in this expanding universe?
Yeah.
So they would also experience the same FLRW.
They do, so the FRW, yes, but the point is that this is really coming from an extra effect only in the tensor sector.
I see.
So one, I don't know if you're familiar, one scenario that can be used to see this is suppose you have you add to GR a scalar field, and you have a coupling which modifies the overall normalization of the action, so like a time evolving Planck mass. Now this will enter in the propagation in the tensor sector. It's like in front of the Ricci scalar, but then opens are not effect. Okay, so this side 0n, I was saying, is you can think of it as the complete analog of W0 WA in the tensor sector. Okay, so we have side 0 is a parameter setting the overall amplitude of the effect, and n parameterizes the time evolution of this exactly as WA. But this is really the most relevant parameter if you want to test GR with gravitational waves, much more than W0, for example. Okay, so that concludes the second important point summarized here. So now with this distance redshift relation, not only we can measure the expansion history, but also test gravity at cosmological scale because we have this modification related to the presence of extra friction. Okay. Now, all this is great news. Unfortunately, if you remember my very first or second slide, I actually said one very important thing. So after all this excitement, is that this combination of mass and redshift is what we measure from gravitational observatories. So there is no way to get the redshift directly from the signal, which is, of course, the second basic ingredient that you need to build a sort of Hubble diagram with these sources, right? And so now this is where a lot of effort in the community is actually put. So to find ways to do this kind of tests with gravitational waves. And that's what I'm going to discuss in the next part. So maybe if there are other questions on this introductory part, I can take them now. This is a kind of a summary.
So the time dependence that goes into the Xi parameterization, where it's 1 over 1 plus z to the n.
Yes.
Is that just a choice? Was there any motivation behind that particular transition?
Yes, so the motivation is that basically, so that's so the effect is something that accumulates over during the propagation of the wave. So the idea is that these now, if you take the z goes to infinity limit, it saturates because it's an integral. It's written. Yeah. It's an integral from 0 to z, where z is the redshift of the source. So if you carry on this integral to high redshift, at a certain point the effect saturates and it goes to a constant, which is psi naught. That's the idea. Whereas if you go at redshift 0, you don't see anything because it accumulates during the propagation, and which is what happens here if you set the z to 0. So then sorry.
Go on.
Then the precise shape of the transition is actually captured phenomenologically by this n. What has been checked is that this works for large classes of theories, except a few subsets that are very peculiar, like by gravity, where you have two metrics, they exchange energy, so this thing can oscillate depending on the energy exchange. So that's a bit more complicated, but otherwise it's a good fit.
So the limits, I completely understand. I was asking exactly about that transition bit. You said it's been checked against a large class of theories.
Yes, it's not a fundamental motivation, I agree.
But so it was checked against.
You can compute in some theories. You can compute this effect. Right?
I mean, you could do this in Horndeski gravity,
Exactly.
for example, but it would depend entirely on what you chose for your Horndeski Lagrangian.
Absolutely.
So
But
I'm not
what
sure
you can do is to map the coefficients into psi 0. So given a theory, you can say take an f of r with an fr naught as a free parameter. You can map this into psi 0. So now, if you constrain psi 0, you would go back and check if it's not.
Sure.
For the specific form of the time evolution, it's a choice motivated by an analogy with W0, WA, and sort of linear expansion in redshift. Of course, the precise shape is still debatable. It's also true that it's a lot subdominant with respect to psi 0. So psi 0 is really the parameter that you constrain well, and then the exact shape of the transition is much more difficult. Okay. So for the moment, I think we can live with it.
Sure.
If in 10, 15 years you want to tell me, okay, let's, for example, try to constrain some DOS theories or bi-gravity theories with n, then we need to.
Sure. I mean, so I could cook up a Horndeski theory that did anything I wanted.
Yeah, exactly.
So, like the fact that there's a mapping from Horndeski to this to something like a Xi parameterization doesn't itself
No,
constrain that form.
I agree.
But I agree that probably if you go plug in something safe like an f of r model,
For
right,
reasonable,
maybe
yeah,
it's a
exactly.
good
For at the moment, for reasonable theories,
Okay.
it's under control. And then there's a second philosophy that I can. So, exactly in analogy with this, you can also be completely agnostic and say I constrain these two parameters, and then, to capture overall, if we can have this kind of effects like W0, WA, right? So a general effective parameterization, or even G effective. G effective, you can constrain it, define it independently on any fundamental model and constrain it. So you say any theory should cope with the fact that G effective should not evolve in time more than some bound that we cannot fully get. But then, of course, you will need to ask the question, okay, but what are the theories that predict the specific form? So there's always a balance between.
Thanks. Can I ask, sorry, a quick question? What's the I know there is one, but the justification, you ignore any change in the generation of the signal due to the modification to gravity. Is it because it's just a completely different length scale, or what? Can you? I remember I've read this, and I think it was in one of Tess's papers, but I can't remember what the answer was.
No, of course. So the idea here is that this is only time dependent. So you have a wave generated in the local wave zone, which is not affected by changes in GR, and then you constrain the propagation. So, for example, typically what you require is that your modifications of gravity recover GR near a strong gravitational field, for example, in the solar system.
So, like due to screening or something.
Exactly,
like that.
that's one scenario. There are other possible modifications to this. The question would be, like a mass term here, this is constrained by the waveform by LIGO data. You could say, okay, this is C will be different from one, but this is constrained by GW 17. The exception to this is if you have a frequency dependence here, in which case the waveform would be modified, and then you can ask Tessa. Yes. No. So did I put it? Yeah. Yes. So it was studied very recently for Lisa Force, the even more complicated case where this is a function of frequency, and in that case you need to compute the effect on the waveform and do the okay. Good. So let's move on. So I mentioned no redshift. Okay. So how do we get the redshift information? This is a intentionally dense slide to convey the message that there is a lot of interest and effort in this field. I'm going to comment this a bit more. So of course, the easiest way to go is if you can associate an electromagnetic counterpart to a gravitational wave source, right? So by detecting a signal jointly to your gravitational wave. What's the problem? First, only a tiny fraction of the overall sources are expected to emit an electromagnetic signal. So black holes typically do not, which are the majority. For the moment, we have like 3 neutron stars in 90 detected events, and only one with a counterpart. 1.5 because there's a debated association. You can ask me later about that, but I take one. Second point, so if you want to test this side zero effect, this effect evolves with redshift. So you need high redshift sources, which are particularly difficult, even if they emit, particularly difficult to catch. And then all this depends crucially on what your electromagnetic experiments will be by the time the observatories are on. So you need to have telescope time to point it, etc. So it makes sense to explore this problem further, and the way to go is we cannot associate one by one an event to a counterpart, but we can do a statistical analysis of the population. So really the way sources are distributed in matter, redshift, etc. And if at the statistical level we can add some information on this, we can hope to break these degeneracies. I'm going to be concrete in a second, but this is the basic idea, and the methods that have been applied and I'm going to discuss is using galaxy catalog or the probability that a black hole has a certain mass. Okay, many others have been put forward and proposed, so I'm going to comment on some which I worked on or I'm working on in the final part, and then comment also on the rest before concluding. Okay. Now, talking about populations, the nice thing is that if we look at the timeline of the number of detections, so in a few years we moved from a situation in which we called the single source by name, we knew everything about it, to today where we are around 90 sources, with a catalog of around 90 sources detected. So we are really jumping from event analysis to a level where we can actually start applying these techniques to a catalog, okay? Okay, this is a bit technical, so if you're not interested in this, you can stand by for a second, but the tool to analyze populations, I think it's still interesting to have an idea. It's called the hierarchical inference. Let's see that this, I wrote the kind of likelihood or gravitational wave data that we have to evaluate. So suppose lambda are your parameters that you want to constrain. So for example, H naught, etc. Now what we start from is the likelihood of each single event in the gravitational wave catalog, okay? It has theta, the parameters of the event, masses, distance, or whatever. And the idea is that we impose a prior at the level of population, giving the probability that the single parameters of the event has a given value, given the cosmological and parameters and parameters describing the population. Okay, and then we can marginalize over the single event sources and carry on a global inference. The complicated thing, which is also hidden here, but we must keep it in mind, is that when you analyze the population, you must take into account the fact that the experiments do not see everything around, okay? Or they can see different things differently. For example, a heavier black hole will be more likely observed by LIGO than a lighter one, or a close by source will be louder, so more easily observed than something far away. And this information must be put in the statistical model, otherwise we get bias measurement. This is called selection bias, also in astronomy, etc. It's very important. This is to say that to evaluate it, we must model the population and compute what is the fraction of sources that we expect to see. Okay, so this requires some knowledge of the population, but okay, of course, the population of binary black holes we are starting studying now, right? So we don't know strong a priori distributions for it. So that's very complicated. But let's try to move to some concrete ideas. So I talk in historical order. So this was put forward by Schutz in the 80s. So the one straightforward, more or less, at least on pen and paper idea will be, gravitational waves will have a localization region. This banana shape is the first gravitational wave event detected. You can take a galaxy catalog and superimpose to it. So you have a set of candidates to be the host, and you can statistically associate the host to all the galaxies there. If you do it for many gravitational wave events, eventually the information will pile up to give, the correct answer for the value, for example, of H naught. What's the problem? So when I started my postdoc in Geneva, we started thinking of applying this method to modify gravitational wave propagation and H naught, which was not the first time. So we wrote our own code. It's there to do this kind of analysis. It was painful, but interesting. So the difficulties here are, of course, if the catalog is not complete, so if you have a few galaxies or not sufficient coverage of the galaxy field, this is not applicable. by definition. So one thing we did is this completeness of the catalog can depend a lot on the direction in the sky, depending on the survey. This is a Jelpitz map of the catalog we use. For example, if you see this black stripe is the galactic plane where you don't see anything, so you need to do something for that. One thing we did is to include this angular dependence and then work hard to add the information on the missing galaxies in order not to bias the measurement. I'm happy to discuss technicalities later. That was just to sketch the idea. The second thing is a selection effect, as I said. What we did here is to include in their computation the possibility of just selecting gravitational wave events falling in complete regions of the catalog, which can be done, but it must be taken into account in computing the possible bias that this induces and correcting for it. So all this is complicated, and all these calculations need to assume something to simulate these sources, these expected sources, so an astrophysical distribution, which is the difficult part. Now, the good news is that models of the population of binary black holes also can inform us on cosmology independently of a galaxy catalog. So let me move to the second thing I will try to apply. The idea is that now we measure the detector frame mass. Okay, of course we don't know the individual mass of an event. That will be too lucky. But what we can use is to model the probability distribution for a black hole having a certain mass. Okay, now if this probability is not flat, so if it carries, in particular, if it has what we call features, so scales where something happens, this can really statistically break the degeneracy. Okay, and the idea is that in particular for stellar origin black holes, what we expect is that above a certain scale, around 40 solar masses, the probability should drop because if the progenitor stars are too massive, then there is a final explosion that leaves no remnant, which is called the pairing stability supernova process. So if you see here, this dotted line is a model of the probability for the heavier black hole to have a given mass. So here we include a drop in this, and now these are the actual events in the catalog. So in the events we see, and there is a kind of pile up of events around here and then a drop. Okay, of course this is phenomenological. We don't know the position of the scale, right? And there are two things. So if we knew it perfectly, then we could use it to infer H0 or Psi0 statistically, but it's also the way around. So if I change the cosmology and use the wrong one, the reconstruction of its position will be shifted. So eventually what you have to do is to infer everything together. So we wrote our own code to do all these, including H0 and modify the gravitational wave propagation. So now let's see what happens when we go to real data. I will always show two cases. One is we fix H0 to Planck, and we try to constrain modified gravitational wave propagation. And the second is I fix the GR as my model. So psi 0 has the GR value, which is 1. Didn't say that before. And I try to constrain H0 because the catalog is limited, so the statistical power is what it is. So let's start by H0, which is here. Let's start by both. So what we do is we do detect the presence of this scale, which we call M break in this model, so where the probability drops, okay, and it's consistent in the two cases. Then for H0, of course, the constraint is very, very broad, but the good news is it's not flat. So there is really a bulk of probability around the correct, hopefully, value. So it shows that you can really get information with this method. But if we look at psi0, this is much more exciting to me because we do get a larger constraint, of course. So remember, GR is 1. But the thing is that before this, based on data, psi0 would have been even 5, okay? because it's something you can bound only by this effect. So, okay, this is broad, but it's also the best we can do as of now, which I'm pretty happy about. Okay, so that's what we learn from. Observe also that gamma is the parameter describing how the black hole merger rate evolves with redshift, which is also affected. This is really hard, but basically unbound if you open up the parameter space to psi 0, because psi 0 changes with the shape. So the two are difficult. So this is a large effect. Okay, you see the correlation direction is very well seen in this plane. Okay, so that's it. Then the second thing we can do is now we take these population parameters. So now we have some best fit for the distribution of masses and redshift, and we use it to model the population for computing selection effects when correlating with galaxies. Okay, so now the thing is we don't have the computational power to do a global inference. So in this case, we fix the population parameters to what we found, and then we evaluate the posterior only for psi 0 or h0 in the two cases. Sorry, but that's the best we can do. You know? So now here, psi 0, you see this is very difficult. The sources are not many. The colored lines are the individual contributions from individual events. I take only events falling in complete regions of the catalog, which unfortunately limits the choice to a few. Okay, and then so the constraint is largely prior dominated, and the gray band is the effect of changing the population parameters within the uncertainties that we got from the. So it's at least it's consistent, but the best we can do is to treat this as a systematic uncertainty and show how much this will shift. Not shifting the others. For H0, this is on the bottom. Unfortunately, it's yeah, I should have bigger, but the thing is the black result includes the only source with counterpart that we detected, and so this will be the result from counterpart alone. There's a dotted line here, but this is to say the counterpart dominates, of course. The role of dark sirens for the moment is that they lower the tail of the distribution, so they improve the constraint from counterpart alone by some 20%, which is I wouldn't throw it away, but this is driven by the single joint detection that we have. If you want numbers, this is the one I get. We get it's basically the same as the one found by the LIGO-Virgo collaboration. So it's the state of the art is a 10-15% constraint if you want from Gravitational-wave. Okay. So to wrap up this part, I put here together the measurements for you to see. Now, if I go back to that timeline, you know, and look at the size of catalogs and accuracy that we can get on psi naught and h naught, you know, all this is dominated by statistical uncertainty. So large errors on the measurements of gravitational waves and small sample size. Okay, so and this error dominates also systematics related to the best way you can model the population, etc. But still, this result is a sort of proof of principle that the methods work, and also the best we can say now about gravitational wave propagation, and also H naught, well, H naught has been done, of course, by LIGO and Virgo, so we're not the only nor the first one to do it, but it's that is the latest we got. Now, if I think about you know, enlarging this a bit, we will have so LIGO and Virgo will have more observing runs in the near future. So now we need to start thinking about the fact that the statistical uncertainty will shrink, okay? And so this interplay with astrophysics will become more relevant, in my opinion. And so that's where a lot of effort should be put, or the one direction to go. in the short term. Okay. So with this, I think, yeah, I completed this part about applications to data. And in the final part, I would like to discuss some perspective for the more far future. So maybe if there are quick questions on this part, I could also take some now.
No, I've always got a question over here. Actually, that plot in the bottom right, and I am struggling to read the label a little bit with
Yeah,
my
sorry.
terrible eyes.
So now the red is the posterior from population analysis. So driven by the mass scaling, the distribution. The other is the one by correlating with the galaxy catalog. And the band is the effect of systematic uncertainty in the population parameters.
Okay. And so I should read nothing into the different, I don't know, their peaks are marginally different, they're just quite different shapes. So are they showing, what would it take for them to show any kind of, I don't know, what would it mean if they start the question again?
Don't overlap.
Yeah, and I can see straight away it's not significant, but would that point to a particular kind of inconsistency in the analysis if that got worse? Or
my worry, so this is really broad and you need to model selection effects and catalog completeness very carefully first. Second, the events that we have here are very few. So, and the ones at high redshift really are the ones important for site 0. So all this is really hard to measure. So for now, I will take these as broad, largely uninformative constraints, like almost a proof of principle. So for the moment, I'm not worried. But what I'm hoping is that, you know, with a few more well-localized events, then this will start really showing something better.
Okay. This may be a really stupid question because I don't know anything about this analysis, but is it possible to do it blind? Should you be doing it blind? Can you do it blind?
Blind with respect to?
So that you don't kind of like know what your H0 number is until you kind of like press the button, you know, like, is there any way to, for
if that's what you mean,
bias?
so here we use the flat prior on H0.
I mean, when you're doing the population model, do you kind of tweak the population model to give you, is that,
No, in that, so when we do the population model, all the priors are flat and quite broad. So in that sense, that's what I meant when I showed, when I showed these saying, okay, not great, but at least it's, it shows because the prior here is flat and also on all the other parameters, it's completely flat and between, H0 20 and 200. So it's, it's really some information that comes from the population.
I guess my worry is like, how much can you kind of sort of, like, what value you're aiming for, or I guess two values that you might be aiming for, like to what extent can that creep into your analysis?
The relevant field for worrying about that is counterparts and catalogs. In that you're completely right, because now maybe in the discussion I can show the story of the debated counterpart, because it's very instructive in this respect. But then how does DES look for possible counterparts? They take so gravitational waves give you a luminosity distance. So they compute the redshift expected with fixing H0 to something we expect, and then they look at that redshift plus minus something. But now if you want to measure psi naught, but then maybe you miss the counterpart because you don't point the telescope to the right spot. So yes, if you really believe in that, you should enlarge your search. For H0, it's true that taking a flat prior so broad is basically an academic exercise, because we know that it should be between 65 and 75. So in the end, it's less worrisome if you only have that. But it's you are right. It's in that it's relevant. Also, when correlating to the galaxy catalog, you should take the region where you look for galaxies broad enough to encompass all possible choices of prior in your analysis. Otherwise, you bias the measurement.
Yeah.
Very good point.
Maybe I have a question. So why don't you measure psi naught and h naught at the same time without fixing one of them?
With this data, the answer is due to limited sample size. So we can do it, so this error, for example, would increase by some amount because it's really, so the idea here was to have a first idea of how much this method would work. So in this context, the principle would be, in an ideal situation, we would have a global analysis of CMB, BAO, and gravitational waves, and then typically the CMB will fix H naught, and then psi naught will be constrained. So now we didn't do a global analysis, but that's for the moment fixing H naught to the Planck value here or putting a prior with the Planck width, etc., is exactly the same thing because these errors are brought due to uncertainties in gravitational waves, but you are right that that's the direction to go. So when we have more data, we will. I have some forecasts later if you want to see the effect. Of course, psi 0 and H naught will be a bit correlated, but the evolution in redshift in psi will break this correlation and allows to measure both dimensions.
Thank you.
Okay, great. So how much do we have?
8 minutes.
Okay.
We've also been like asking a lot of questions.
Yes.
Yeah, okay.
Yeah,
So now the last part is more about the far future, so we can have more room for speculations because we don't have data to check. No, the idea is if now I extend this timeline by 10 years, as you all know, we have next generation experiments planned. So there is ESA flying in space. I'm not going to talk about that today. I'm going to focus about ground-based detectors. So the idea here is that this will be another paradigm shift, because if you look at the expected sample size, there are several orders of magnitude differences, and if you look at the accuracy on, say, H naught or psi naught, independently of the probe, etc., the aim is to get to % or sub% level. So this will be precision gravitational wave cosmology. So completely different. So the idea is how do all these techniques scale to next generation? Can we find other, maybe that rely less on these population complications and so on? Okay, so for ground-based, the expectation should be to have, there is this design for the Einstein telescope, which is a detector based in Europe with a triangular configuration, okay? Which has a lot of nice properties that I can discuss later if you're interested. And then the Cosmic Explorer that should be 2 interferometers L, so like LIGO, but a lot bigger. Okay, and this, so I put here the references to the science cases for you if you want to. So the thing is, this is really at the beginning stage. So we are trying to characterize their science now. So the first thing is there's a lot of effort in the community to forecast the parameter estimation capabilities of these experiments related to individual events in the form normally of feature codes for parameter estimation. We are working on one. There's a lot of groups converging on similar results. So for binary black holes, for example, the impressive thing is the rate. You could get up to 10 to the 5 area. This is a distribution of so this is a bit small, but I can comment. This is a redshift, and this is the relative error on the luminosity distance, which is what's interesting for cosmology. And so now you can't see it probably, but there's a lot of, or a very good fraction of the sources that can be, localized at better than 10% relative error up to redshift more than 10. And this is the cumulative distribution of the 90% angular localization area, and also here you don't see the tails, but there are tails with a few percent or per mil of the sources which are localized very well. So that's a great perspective for the aficionados. So for the experts, there's also the possibility of including higher harmonics in the detection, which breaks the degeneracy between inclination and distance in the gravitational wave signal and improves a lot the localization capabilities. Okay, since we don't have a lot of time, I will mention this briefly, and again, I can discuss it later. One idea that we discussed in that paper last year is that, so among these many black holes, a fraction of these will be lensed, strongly lensed, so the same way as in electromagnetic observation. And now, if you think, if you remember this difference between gravitational and electromagnetic distance, suppose we take one event with 4 images, okay? Now, these you can reconstruct the properties completely. The idea is that now you will have 4 measurements of the gravitational distance, okay, by the 4 images, but you can also measure the time delays between them. And the time delays are sensitive to the electromagnetic distance. So you have a standard siren without the counterpart, because you have a gravitational plus electromagnetic measurement in one. And, then you can really test with this system, even H0 and psi, this is H0, psi0 together without imposing any external prior or other data set. Okay, it's a bit of a speculation, but it's I think it's a very nice idea. With one source, this is redshift, so you go to redshift higher than 2 with better than 10% precision, you can really get a few sigma measurement from one single event. That was really nice to see. Okay, to conclude, the thing is there will be other sources. Now I've talked about black holes. One great thing that these instruments can do is really to measure a lot of neutron star systems, because they are more sensitive at low frequencies. And in particular for neutron stars, we have the possibility that the signal stays in the detectable band for so long that the Earth will have rotated by the time the merger ends. And so the relative position of source and detector will change during the time the signal stays in the band. So you get a modulation, and this breaks the degeneracy between position and distance partially. But the idea is that with a single ET, this is the localization area for single ET. And there is a fraction of sources, this is 10 to the -2, that you can actually localize, not perfectly, but this will be impossible without this effect. And because normally the localization is given by triangulation, so you need 2 or more detectors. And this orange curve is 1, okay, 1 triangle. So for these rates, even here 10 to the 5, 10 to the 6 years. So the idea is, for example, you can use the same techniques that I described for binary black holes, because now the mass distribution of neutron stars is narrow, in the sense that it's limited up to a few solar masses. And so this is an illustration of the same technique that I discussed before for black holes. So the idea is these are redshift beams. If you try to reconstruct the mass function in each redshift beam, okay? Now this is the answer in GR, and the colored distributions are what you would get if gravity was modified, but you will not include that effect. So you will get a coherent deformation of the reconstruction, and now the difference between the correct, the dashed and colored distribution really constrains psi 0. So technically it's the same as what we did for binary black holes, but with different sources, hopefully less subject to systematics in the modeling of the population. Okay, so that's, we are working on that now. Okay, so final thoughts before concluding, also to give some perspective. Now, I discussed some ideas because I worked on them, I like them, etc. but the landscape is very rich as I was anticipated. So don't forget that other methods are around, in particular some consist in finding effects, maybe higher PN, etc., that break the mass redshift degeneracy. I like the idea of using, for example, now we can associate statistically the host to a galaxy, but we can also do two-point functions to the correlator and really see how it overlaps between galaxies and gravitational waves. We can combine these techniques. For example, in this work recently, they said, okay, let's try to see what we can learn from the distribution of all the objects in mass, so black holes and neutron stars, the mass spectrum. The final thing I must also comment on, to be fair, are counterparts, because so the talk was about dark sirens, and okay, I tried to convince you that it's very interesting, but you know, of course, telescopes are there. So counterparts are very powerful. The point is they depend very much on the status of electromagnetic experiments. So it's a bit difficult to forecast what we will be able to do with this next generation, because we need to know which experiments will be operative. But one proposed one is called the Prisbius. So for example, in this paper a few years ago, they tried to forecast the rate of coincident detections, and they showed so in an optimistic detector configuration with TC plus these, we could have up to a few hundreds, up to 100 per year roughly. So with this, you can still hope to reach percent or sub-percent constraints on these parameters. But of course, if you compare to the rate, so 100 per year compared to 10 to the 5, dark sirens, to me, this motivates the interest in exploiting the full spectrum of detected sources. And the second motivation is this, you don't see it probably, sorry, but this is redshift, and this is 2. So the forecasted, and those are the coincident detection, the distribution in redshift. So after redshift 2, there is nothing. But if you remember the distribution in redshift of detected sources that I showed before, it went up to redshift 10. So I would like to be able to exploit those sources if possible, because that's, it's maybe I didn't, so this is very important. You can really see all the star formation history through gravitational waves if you go to those redshifts. That would be amazing. Okay, that I can leave with general conclusions to wrap up. I try to go along this timeline. So now the situation now is that these first applications to data are almost at the proof of principle, but for gravitational wave propagation, I'm still quite happy that it's a factor 10 or so improvement of what we knew before. So we have developed our independent pipeline. There is then the LIGO Virgo collaboration that does this analysis. Then in the short term, we should really try to understand what we can do for interplay with astrophysics, while for the future, the landscape is much richer. But there are two things for sure that I want to leave you with. First is, so this huge shift in data is guaranteed, at least for LISA. So we need the techniques to statistical tools scalable to those sizes, etc., to be able to analyze them. And the second is that, besides of any specific interest or what's your favorite technique, etc., the thing that gravitational waves are distance tracers is pretty unique in cosmology, and this will remain besides any any other thing. And the idea is that then we will be able to do precision cosmology, and those sources will be new cornerstone in the picture. So that was the final message, and I can stop here and take questions.
Thank you very much for your talk. Right, we are just past the hour, so I understand if some people have to leave, but we have time for a quick question or two. Is there anyone online who wants to ask a question?